What's up? I'm Munot and welcome to the School of Physics. So today we are going to do gravitation, which is a very interesting topic within a few minutes. From gravitation, questions just come from direct formulas. All you need to do is just know what the formulas mean. Though I'll derive some of those formulas so that you get a better understanding, conceptual understanding. So let's start with gravitation. In gravitation, first of all, let me tell you what a gravitational force is. So these are the two masses, m1 and m2, right? And they are at a distance of r. They are at a distance of r. So what is the force of gravitation? It applies some form of force. This mass applies force on mass m2 and mass m2 applies force on mass m1, and both of these forces are equal. So the formula for this force is G m1 m2 G m1 m2 upon r square. G m1 m2 upon r square, where r is the distance between them. And what is G? G is the universal gravitation constant. G is the universal gravitation constant, and the value of G is 6.67 into 10 to the power minus 11. A lot of people forget its units, so I have arranged the numbers in a descending order. So its units is meter cube second ki power minus 2 and kg ki power minus 1, kg power minus 1. So this is the value of gravitation constant G. Also we need to remember what is the potential energy. So you have seen in the chapter of the work power energy that for conservative forces equals to minus of du by dx, right? Minus by, here we write minus du by dr. When we differentiate, when we integrate, we can find u, which comes out to be, I am writing it directly, it comes out to be minus g m1 m2 by r. Also you need to remember the kinetic energy. The kinetic energy comes out to be, we are not deriving it, you have to remember it. The kinetic energy comes out to be G m1 m2 upon 2r, G m1 m2 upon 2r, and the total energy comes out to be summation of kinetic energy plus potential energy plus kinetic energy is equal to, you add both of these, it comes out to be minus G m1 m2 upon 2r, minus G m1 m2 upon 2r. So guys, you have to remember all of these formulas. Let's move on to the next thing. The next thing that I am going to tell you is about the acceleration due to gravity. So acceleration due to gravity is a very commonly asked question. You know the value of G. So first of all, we'll derive G. Okay. So suppose this is Earth. This is our Mother Earth. Okay. And this is the radius of Earth, and this is the mass of Earth. Now you're this particle, your mass is m. Now what force is Earth applying on you? What gravitation force is Earth applying on you? It is equal to G mass of Earth into your mass upon radius of Earth whole square. G mass of Earth into your mass upon radius of Earth whole square. And what is this? This is the gravitation force. We can write it as mg, where g is the acceleration. So as you know, force is equal to mass into acceleration. So this is acceleration. So this cuts. The value of g, as you know, is 6.67 into 10 to the power minus 11 meter cube second ki power minus 2 kg ki power minus 1. Mass of Earth. Any guesses how heavy the Earth is? in terms of kg. A lot of times in exam papers these data are not given, so I would advise you to remember all of these data: mass of earth, radius of earth. So the mass of earth is 6 into 10 to the power 24 kg. Just imagine 6 into 10 to the power 24 kg, and the radius of earth is 6400 kilometers. So how big our earth is? So mass of earth is 6 into 10 to the power 24 kg, and radius of earth is 6400 kilometer. So from here we get G equals to 9.8 meter per second square. So this is the acceleration due to gravity. Now we'll see the variation in acceleration due to gravity with a lot of factors. So the common factors that can come to my mind is rotation of the earth as we go downwards, variation of G with depth, variation of G with height. So here is the concept that with altitude G decreases, and with altitude G decreases, and also with depth G decreases. So G is the maximum on the surface of the earth. And what is the variation? So with depth, suppose you go edge distance downwards. So at here, if acceleration due to gravity is G here, and if it is G dash here, then G dash is equal to G into 1 minus 2h upon Re. Very simple formula you have to remember. With depth, G dash is equal to G into 1 minus 2h upon Re. With altitude also it decreases with altitude. So suppose you go edge distance upwards from the earth. Now with altitude, the value of the new G dash, the new acceleration due to gravity, here it is G, here it is G dash, will be equal to G dash is equal to G 1 minus h upon Re. Very similar formulas. Here it is 2h, here it is h. Re is the radius of the earth. And what about the rotation of the earth? So the earth, this is the earth, and it is rotating with angular velocity omega. So if you are asked what is the weight that you will actually have when at an angle theta, when you are at an angle theta from the equator, so your actual weight, you have to remember this, your actual weight will be less than mg, and it will be equal to mg minus m omega square r cos square theta. You have to keep this in mind. Direct questions will come, you just have to apply the formula. Okay. What do you know about Earth? Is Earth a perfect sphere? You know it is not a perfect square. It is elliptical in shape. So Earth is elliptical in shape. So another point that I have to mention is radius of Earth is greater than at equator than radius of Earth at poles. So radius of Earth at equator is greater than radius of Earth at poles. How much is the difference? Difference is approximately 21 kilometer. As you know, if we can see from the altitude equation, so the G at poles is going to be greater than G at equator. G at poles is going to be greater than acceleration due to gravity at poles is going to be greater than acceleration due to gravity at the equator. You have to remember this. Now okay, let's talk about satellites now. So satellites, hold on. what do you know about satellites? So in satellites, we'll talk about the orbital velocity, the escape velocity, and also the time period of the satellite, though the time period questions doesn't come much, but escape velocity and orbital velocity are asked. Now I'll first make you imagine what escape velocity and orbital velocity are. So suppose this is our Earth, this is radius of Earth, and at a distance h you are launching a satellite. So what should be the velocity of the satellite around the Earth, the tangential velocity of the satellite around the Earth, so that the satellite orbits the Earth, okay. So as we know, there will be a centrifugal force mv square by r on the satellite, and that force should be provided by gmm by r square, that is the gravitational force. So we equate mv naught square, this is the mass of the satellite, mv naught square upon r plus h, since this is the orbit that we are seeing, upon r plus h is equal to g mm by r square, r plus h square, since this is the circle that we are considering, the new radius becomes r plus h. So here this cuts, what remains is v naught is equal to under root gm upon r plus h. v naught is equal to under root gm upon r plus h. When h is very small as compared to radius of the Earth, this becomes under root gm upon r. The escape velocity formula is under root 2gm by r. So velocity escape, I'll tell you what the velocity escape means, but you have to remember correlating both the formulas, that in here velocity orbital is under root gm by r, direct question will come, and velocity escape will be under root 2gm by r. Now what is escape velocity? I'll teach you what escape velocity is. Escape velocity is the velocity when it is the vertical velocity at which, suppose we have this planet, and here we have a satellite that wants to leave the field of the Earth, and it is at a distance of, so at what velocity should it leave so that it goes away from the influence of the Earth? So what we do in this case is we do kinetic energy plus potential energy of this satellite should be equal to 0. Okay, so this is half mv escape square. What is the potential energy? It is minus g m greater m by r, minus g small m greater m by r equals to 0. So as it is equal to 0, mm cut. So what comes is escape velocity is the under root 2 gm by r. Orbital velocity is under root gm by r. So whenever the vertical velocity at which a satellite leaves the influence of the Earth, that is the total energy becomes 0, is the escape velocity. The next thing that we are going to talk about is time period. So you have to remember the formula of the time period. So if there is a satellite which is revolving around the Earth on, say, at a distance of h from the Earth, if it is revolving on the surface of the Earth, the formula for the time period of the revolution of the satellite around the Earth is very simple. In pendulum, you know the formula of time period, it's 2 pi under root L upon G. So here just you have to do 2 pi under root r upon g, 2 pi under root r of earth upon g. But when it is at a distance h, from the surface of the earth, then the formula becomes a bit complex. But first you remember this, because most of the questions this thing will cover your thing, because h mostly is very small as compared to the radius of the earth. So a lot of objective questions, you can eliminate the options. The detailed formula for this time period, is 2 pi, let me remember, one second, r plus h whole cube by g under root, okay, and here we have 2 pi by r, so 3 by 2, suppose this is r 3 by 2, so r 3 by 2 minus r 1, that is r 1 by 2, so this becomes 3 by 2, okay, so this is r, so it is 2 pi by r plus h whole cube upon g की power 1/2. When h is, see, we can verify when h is less than r, so this becomes r 3 by 2, r 3 by 2 by r is r 1 by 2, okay, so we get the same results. So you have to remember this formula. Next thing that we are going to talk about is Kepler's law, Kepler's 3 laws, and then our gravitation is over. So Kepler's 3 laws, very simple laws. What Kepler said was, law number one, so what happens is, this is an elliptical orbit, now first of all I'll teach you what an ellipse is. An ellipse has a semi-major axis and a semi-minor axis. So this length is 2a, and this length is a, and this length is b. So this is semi-major axis, semi-minor axis, and then there are two focuses. So the first law that Kepler said was that sun lies at the focus of the ellipse, at any focus of the ellipse, and the planets revolve on them. So this is sun, say any of the focus, so this is sun, and this will be the planet revolving around sun in elliptical orbits. The second law was about areas. So suppose I travel from here to, it takes me t time to travel from here to here. It doesn't take me, it takes this planet t time to travel from here to here. Then on some other side, it takes the planet same time t to cover this distance. Then the area covered by the ellipse and the sun at the focus, this area in equal times will be equal. So this is the second law of Kepler. The third law says t square, that time period of revolution around sun in an ellipse is directly proportional to semi-major axis ka whole cube, So this is t square is directly proportional to a cube. When this is a complete circle, this is the time period for the complete ellipse to complete. So for the planet to complete the revolution around the sun. So for a complete circle, right, because a circle is also an ellipse, we have to just remember the formula. The formula is t square is equal to 4 pi square by gm, 4 pi square by gm into 4 pi square by gm into a cube. So this can also be asked, this you just have to apply the direct formula. Okay guys, so this was our chapter Gravitation. I hope you liked it. Please subscribe to my channel. I'll keep on making more videos and helping students. Thank you.